Last class period, we were looking at transformations of functions. We had talked about how adding, multiplying, using negatives, things like that changed graphs. We did the graph of x squared, and we saw some shifting going on when we had this particular one. On the first one, you noticed it moved it left 2. On the second one, you noticed it moved up 2. On this one, you noticed it flipped over the x-axis. On C, you noticed that it made it sort of skinnier, or it stretched it vertically. And on E, you noticed it sort of compressed it, or it flattened it, or you could say it stretched it horizontally. We're going to focus on compression vertically. And then we looked at the same thing with the graph of square root of x. And we noticed a lot of the same kinds of things happening. On A, we noticed again it shifted it left 2. On B, it shifted it up 2. On C, it flipped it over the x-axis. This particular D, where it flipped it over the y-axis, that one was interesting because we didn't have that example when I did the x squared graphs. So if you would come back over here and think about it with me, if you had the graph of x squared, I don't care which one we look at, but the green one here, and you flipped it around the y-axis, what would you notice? So if you take this green graph and you flip it around the y-axis, what do you notice? It's exactly the same, right? So this graph has some symmetry. It's symmetry along the y-axis. So when we flip it around the y-axis, it doesn't actually change, which is why I didn't have an example of that one there. But on the square root of x, it doesn't stay the same. It actually flips and it looks different when we flip it over the y-axis. And then here's where we are from last time. So we're on on E and F. So again, grab your calculator if you have it with you. If not, we'll borrow this one that we found sitting in the classroom and someone else's. Who needs a calculator? Nobody nearby who has one he'd like to borrow. I can't tell you how to use that one, Preston, because I don't have that calculator, but if you guys can figure it out, you're welcome to it. Okay. So if you'll remember, in y1, you're going to put the square root x graph, and then in y2, you would put the 2 square root of x graph for E. And these are my square root of x graphs, and we'll do E. So what happens when you compare the original graph of square root of x to 2 times the square root of x? What kind of imagery would you describe happening? So it looks something like that. Yes, no, maybe? Yeah? So the way we would describe that is much like we saw it when we multiplied 2 with this x squared graph. Again, it's stretched vertically. We take it and we stretch it like this out of shape, okay? Stretch it up. And then when we look at the 1/2, what happens when we look at the 1/2 square root of x? What is it? It's lower, right? It's beneath the green one that I have, right? And again, we would call that a compression. It's not great. Something like this. It has shrunk it or compressed it vertically. So we're going to make some claims about all graphs based on inductive reasoning. The exercise that we've just done is looking at very specific graphs and seeing what happens when we make certain changes. And in fact, the changes that we're seeing happen do work for all graphs. So on the first one, if you were to add x on the inside, we actually did this one. What happened on part A of both of those examples when we added the 2 inside with x? It shifted 2. Do you remember which direction, Karen? It shifted 2 to the left. So when this happened, the graph moves the graph left. And in particular, it's 2, but the reason, of course, it's 2 is because there's a 2 here. So if it were a 7, it would move it left 7, right? So it's whatever that value is that is corresponding on the inside. Now we didn't do the second one. We didn't do -2 on the inside. But if adding 2 moves it left 2, what do you think subtracting 2 would do? It moves it right 2, yeah. Adding 2 moves it left, subtracting 2 moves it right. Okay, again, on number 2, we did the first line of 2. When we added 2 on the end, not inside grouped with x, but on the end of the equation, that was part B for both of our examples. How did the graph change? It moved the graph up 2. We didn't do the other part, but what do you think would happen if I put subtraction of 2 on the outside? It'll move it down 2. You got it. The first part of number 3 we did on both equations. It was part C, the third graph that we did. What happened when we had a negative in front of our equation? Flipped how? Do you remember? It flipped over the x-axis. I'm glad you said it that way too. We had graphs that happened to be starting out above the x-axis, so when they flipped down. But if you had a graph that was below the x-axis and it flipped, it would flip up. So this actually reflects a graph over the x-axis. And we only had one example of the next one. It was on the second part we did when we did the square root of x graph. And it was what we had as part D over here. So when we went from the green side to the blue side, this is also a reflection, but over which axis? The y-axis, yeah. And we talked about why that didn't happen with our x squared graph, why we didn't even look at it. But this is a reflection over the y-axis. And then when we multiply by a value in front of our equation, if the number is large, and I mean bigger than 1, that's pretty broad, but bigger than 1. So there's two categories. This value is either bigger than 1 or this value is between 0 and 1. Okay, so if the value is bigger than 1, then it's a stretch. And we always think about the stretch being vertical. So this is a vertical stretch. And then if it's a fraction between 0 and 1, it shrinks the graph vertically. So we're either stretching it up, stretching it down, like they're stretching it along the y-axis, or we're compressing it like Play-Doh, like a pancake, okay? We're squishing it down along the y-axis. So we're going to do some examples now of how that affects graphs. But before we do, I want to talk to you about the 3 basic graphs that we are going to use for consideration. And the benefit in what we're doing right now is that I no longer need, number 1, 5 points. 3 will be enough. And then I also no longer need to write down the ordered pairs. So those are really beneficial things. Instead, what we're going to do is we're going to take a basic graph that we know. We're going to move it up, down, left, right, stretch, flip, whatever we need to do. But we're not going to do it by plotting points. Okay? So here are our 3 basic equations that we're going to consider for our purposes. The first one and the third one we already looked at. So with the graph of x squared, you know that you have the point at 0, 0, 1, 1, and -1, -1. So these are our 3 points. And a graph of x squared is a shape of a what? A U, right? It's a parabola and it's got a U-type shape. Okay, that to center. So this is the basic shape of x squared. Absolute value x, which is not one that we did for the purposes of our discussion last time, has the same 3 points, the origin, 1, 1, and negative 1, 1. But it isn't the shape of a U, it's the shape of what? A V. So once I actually have my 3 points plotted, I'm going to connect them with basically lines so that I end up with a V shape. And then our third one, we don't even need 3 points. We'll just have 2. Again, it's the origin, and it's 1, 1. And it's the shape of half of a sideways parabola. So it looks like that. That's really thick. Let me try that a little bit different. So we're going to start in each case with one of these 3 graphs, and we're going to manipulate it using those shape-shifting features that we talked about on the previous slide. So here's an example. What is the basic graph, or it's sometimes called the parent graph? Which one of those 3 basic graphs is this? Yeah, the first one. It's the x squared graph, looks like a U, right? Let's talk about what each of these values is doing to it. We'll start at the end. What is the plus 1 doing? How does it change my graph? It moves it up 1. Okay? A number on the outside moves it up or down. Positive moves it up. And then I have the 4 on the inside, and it does say positive 4. How will a 4 move my graph? Yeah, it will move it left. It's kind of a crazy thing because it feels like, we would want to say that it moves it right because it's positive. But whatever happens inside with x does so in the opposite way of our intuition. All right, so this will move it left 4. So what we do is we take the basic functions, it's called a vertex, that point at the bottom, which would have been right here. And we manipulate it exactly the way we've put words to it on our screen. We need to move it left 4 and up 1. So left 4 and up 1 puts me here. And then, because I don't have any more changes, I've already taken care of the left and the up, right? I already did those 2 facts right there. The other 2 points will go up and over from there, just like they did before. I don't have any stretching or reflecting or anything like that going on. So my other 2 points end up being here and here, and then I connect them in the shape of a U. There are 3 points plotted, but I didn't write down ordered pairs for 3 points. Do you see the difference? I did it based on these shifts that are going on. Any question on that one?
Yeah, I'm not understanding the other 2 points.
Okay, so on this graph right here, I had 3 points, right? 0, 0. That's not a good color. Let me try this again. And then I have this point that's up 1 and to the right and up 1 and to the left. And that pattern always happens if I don't have any other shifting going on. So like if I multiply it by 2, like I did on one of those at the beginning, instead of going up 1 and right, I'm going to go up 2 and right. And if it were multiplied by 1/2, I'd go up 1/2 and right.
Okay.
That's what I would do. And we'll see an example of that in a minute. Any other questions? Okay, let's try another one. How many transformations do you see to this graph? Three, right? There are 3 numbers that are not normally there. What is my parent graph or my basic graph? What is it? Yeah, y equals the absolute value of x, just that part. Okay, There are, like you said though, 3 numbers here. There's a 3 at the beginning, there's a positive 2 in the middle, and there's a negative 4 at the end. Let's just go from left to right. The 3 at the beginning, what will that do to my graph? It will stretch it. Right, this is a vertical, you don't have to write the word vertical, but I'm going to keep reminding you, it's a vertical stretch. How about the 2 inside? Yep, it will move it left 2. And then how about that 4 at the end? Close. What do you say, L'Oreal? It'll be down 4, you're right. That one's down. So anything that's happening on the outside moves it up or down, so this one will be down 4. Okay, so as we're working on this, the easiest thing to do first is the upright, up, down, left, right ones, okay? So this one first says left 2, down 4. So I normally am at the origin. I'm going to move left 2 and down 4, which puts me right here. Okay, that's my first change. There's 2 changes there, but you can operate them like they're one. I can move left and I can move down at the same time. Everybody good with that? Now the next thing said it was a stretch of 3. So Karen and I were talking about how we got those other 2 points, and I talked about the fact that it's always up 1 and out 1 for absolute value. Well, I did it for x squared graphs, but it's always that way for absolute value graphs as well, right? Up 1 and over 1 to the left and the right. But this has a vertical stretch by a factor of 3. So what that means is instead of going up 1 and right and left 1, I'm going to go up 3 and right and left 1. Okay? So over here, from where I am, I'm going to go up 3 and right 1, up 3 and left 1. And that's where they get plotted. You don't have to identify them as like ordered pairs, write it out, but they need to be plotted. Okay, that's the scale of what's going on. I have this vertical stretch of 3. And it is an absolute value graph, so the shape is a V, as opposed to the U that we had on the last one, right? So we're going to connect our dots in the shape of a V, and we're done. Any questions on that one?
So remember, like, what do you do for the next 2 points? You just go one.
You always go 1 to the left, 1 to the right, yeah. Of course, the caveat to that is the square root of x graph, because we don't go right and left, we only go right. So on that one, we'll only go to the right when we do it. All right, so the parent graph here, of course, is my square root of x graph. How many transformations do you see on this one? There are 2. There's a 2 at the end, and there's a negative inside. Okay, so there's 2 possibilities when it's negative. It's on the outside or it's on the inside. When the negative's on the inside, how will it flip? Will it flip down or vertically, right, like this, over the x-axis? Or will it flip around the y-axis? It's a y-axis, right? So this is a reflection. So I'm going to say it reflects over y. How about the 2 at the end? What does that do? Yeah, it's up 2. Good job. Okay, so normally I'm at the origin. For all of them, I start with the origin. But this says from the origin I need to do what? I need to go up 2, right? So I'm going to be here instead. And then normally, I'm going to sketch it in yellow here. Normally the graph looks like this, roughly speaking. But it's going to reflect, and how's it going to reflect from there? Down, because it's currently in the, it's currently reflected up. And it's going to reflect down from exactly where it is. So what does that mean? Well, it means that I'm going to be drawing it right here. It's going to be the other half of the missing part of that parabola. Oh, I'm sorry, not down. I keep saying the wrong word. Left is what I meant to say. This way. We said it was over the y-axis. I'm so sorry. Like that. So it's going to reflect across the y-axis. If we're reflecting across the x-axis, it would complete that parabola, which is what I was trying to draw. So this yellow, not really here. I'll erase it. And I didn't actually plot it, but it's there. Here's my other point that I should have plotted. Up one and left one. My bad. Okay. I think all my details are there. Any questions? Okay, so we've got these three basic graphs, depending on what resources and textbooks you use. There's a couple other basic graphs that show up. However, we don't actually have to have any of those graphs to actually be able to do any of these transformations. We could have just a random graph given to us. So we're going to start on here with a random graph given to us. Looks like whatever it looks like. This kind of looks like an absolute value that's already in a funny shape, right? It's flipped down, it's shifted left, and it's shifted up. It's already here. So what it's asking us to do, yeah, I've got it written in there, right? What it's asking us to do on each part is to make a change. So on this one, I see a negative drawn in front. How does that change my graph? I'll start it out for you. It's a reflection. That's what negatives do. How does it reflect? Will it reflect over x or y? What do you have, Michaela? Yeah. This reflects over the x-axis. And if you're actually reflecting over the x-axis, it means however far up you are, you will now be down that far. So let's take a look at a specific point. How far up is this point right now? Can you tell from where you're sitting? It's 5 up. So when it gets reflected, it will go all the way down to being 5 below. That's a store. Have you guys been there? I was there this weekend. One of the many kid activities that happened. Okay. And this piece would shift also, right? As it gets flipped down, of course it has to hit that corner point that I just made. And it looks like it's going to be, roughly speaking, here. Feel free as you're working to fold your paper so that you can get it to match up well. Right? It's a reflection. Tracing paper, if you want, you can use tracing paper, it's great. Or just really thin copy paper. It's just as good as tracing paper. And then the other piece looks like it's right here. And we can double check. You could use the endpoints if you wanted to. This one is up 2. This point's down 2, right? And over here, this point's up 1. Oh, my graph over here is not so very good. I'm going to fix it. This one's up 1, so this one should be down 1. I'll reconnect them. That's better. It's okay? That's a reflection over the x-axis. So what's the second one then? Yeah, it's over the y-axis. So this is a reflects that it reflects over the y-axis. Okay, so if a point's already on the y-axis, it doesn't move. That point's going to stay put. You can't reflect it over y when it's on y. But every other point is going to move. This point is currently to the right how many? 4. And we're going to reflect it to the left 4. So it will come over here. That's where it's going. So this piece, when I connect it, is a mirror image of this piece, right? Reflected to the left. This piece is at a height of 5. We already said that a moment ago. But it's all the way 4 to the left. So when it reflects, it will flip to 4 to the right. So it flips to here. And again, we'll continue that line up to there now. And this piece is, ooh, it's 7 to the left. So now it will be 7 to the right at that same height. Should be here. And I would connect my points here. It almost looks like a spider now. I need a few more legs. But that's the reflection, and they overlap. I mean, this reflection happens to overlap. The first one didn't. So it is possible to have overlapping reflections. If it bothers you to draw them on the same graph, if you would like, you can sketch them on a different graph. You're going to have to draw extra in order to make that work and make sure that you count things appropriately and all that good stuff. But if that makes you feel more comfortable with how to do it, then you can do that. Number 5. Let's take a look at these things. What does the 2 on the outside do? It's a stretch. What does the negative 3 on the inside do? Right. It is a shift to the right 3. So, I'm going to pick up this whole graph and I'm going to move it 3 to the right. All right? And I'm going to do this in 2 stages because there's 2 different transformations going on, and I find it very difficult to do 2 transformations personally at the same time. So if I move these 3 to the right, then this ordered pair moves 3 to the right to here. This one right here moves 3 to the right, 1, 2, 3 here. And get another color. This point moves 3 to the right here. And if I connect the points, I've got the same image 3 to the right. That's an in-between step. Are you with me? I have not finished the problem. In-between step. And then I need to multiply everything by 3. It's supposed to be stretched. So everything is 3 further away than it was before from the x-axis. It's a vertical stretch. So if I'm on the x-axis, I stay put. So my green dot is not moving. But the blue dot and the purple dot, they are getting multiplied by 3. Where am I right now on my blue dot? What's my y value here? It's negative 4. So if I multiply negative 4 by 3, what do I have? Negative 12, which is not on my screen. I'm going to have to extend my axis down here, unfortunately. I even copied this particular picture from your textbook. So this is 9, 10, 11, 12. So here's negative 12. So it will extend clear down to here. This value is only negative what? Negative 2. So if I extend it, negative 2 times 3 would be negative. Guys, I'm looking at y-axis, y values. That's what I'm looking at. So this is a y value of negative 2. Is everybody okay with that?
Why are we multiplying by 3?
Because it was by 2. No wonder you're looking at me funny. Oh, and then I would be on my graph, which makes more sense. Thank you, Lauren. Multiply by 2. Then it'll work on my graph. How about there? Is that better? Thanks. Now let's multiply by negative 2. Or multiply our negative 2 by 2. So I'm at negative 4. Here we are. There's negative 4. And the green dot didn't move, right? So this would be my final graph right here. And I'll color it in a different color. Maybe I'll do it in red just to identify it better. So here's what I have. My red graph is the final graph. It is stretched down. And technically up, but it doesn't go up beyond where the x-axis already is. How about the second one? What does this plus 1 do here? It moves it up 1. And the negative? It's a reflection first. Does it reflect over x or over y? X. When it's a negative on the outside, it reflects over x. We can do the reflection first because, in fact, it's a good idea to do the reflection first because we move from the from the inside out, and the negative is most closely associated with our function. So let's reflect first, and then we'll shift up. So if we reflect first over the x-axis, everything that's in the bottom of my graph now is going to reflect up, right? I'm going to have everything down right now is down beneath the x-axis, and it's going to reflect to being above the x-axis. The point that's on the x-axis doesn't change. This point's 2 down, so now it'll be 2 up. And this point's 4 down, so now it'll be 4 up. So my first change puts me here. That's a reflection. And then I'll use red as my final graph again. And then I'm going to take everything and I'm going to move it up. So I'm going to shift up 1 here, up 1 here, and up 1 here. Reconnect them for that graph.
On our homework, do you want us to do like 3 graphs or 2 graphs?
If you can do it in 2, like only draw it 1 time, and some of them you might be able to, especially if you're only shifting like left and right, up and down. That's doable in one particular point. But the stretches and the reflections and intermixed with the shifting, it's really difficult to do all at the same time. So I would encourage you to do it. I'm not going to require it. If you can do it in one fell swoop to final point, that's fine. But oftentimes it's just going to make it more difficult to get it right because you're going to miss something along the way. I would encourage you to use colors so that I can tell, or you can tell me where your final graph is if you're making multiple graphs on there like I have. Okay, we have one more example in this section. What we actually have is a picture. The graph in blue is translated. And the blue graph is actually got an equation of f of x equals negative 1/2 x squared. Like that's the equation of the blue graph. We'd like to figure out an equation for how h, or not h, yeah, it's called h on your graph and then I wrote g up here, so let's be consistent. This is h. How this new graph h is obtained. So we need to figure out, are there any reflections? Are there any stretches? Is there any shifting left, right, up, and down? What is going on with my graph? So tell me some of the things you see. What do you see that has been changed when you go from the blue graph to the red graph? Okay, so down 3, and over, do you mean by right or left? Left 2. So that takes care of this point going to that point. Does everybody agree with that? Just the vertex itself, you can count and you can do that. The next question is, are there any reflections? No, it's still in the same direction, right? It was opening downward, it's still opening downward. How about stretching? Is there anything stretching going on? So it's harder to see than when you actually are trying to stretch it yourself. But remember, if you go left down, if you go left and right and you go down 1/2, which you would because this says 1/2, right? Is that what's happening on this graph? If this one goes left and right, does it also go down 1/2? It does. Yeah? It's also down 1/2. So there's actually not any stretching going on from the blue graph to the red graph. They're the same shape. So what does that mean? Well, it means that that value at the front, that negative 1/2, is the same. It's the same as it was on the original graph. It's negative because it's opening down, really. It's the 1/2 because it's that same 1 over 1 and then down 1/2. But I need to manipulate it so that it moves it left 2 and down 3. Let's start with the down 3. How do I get something to move down 3? Subtract 3. Where? Inside with x or at the very end? At the very end. So down 3 means I'm going to put subtraction of 3 here. how do we get something to move left 2? X plus 2, and that's inside grouped with X, right? Hugging tightly with X. And when I say that, I mean that it has to be like right by X, not by X squared. You guys said add 2 so that it would look like this, and then the square would come after the addition. That's how I would get it to move left 2. And could you check this one in your calculator to make sure you got the equation right? You could, and if you don't happen to have a calculator that graphs, you could graph it online. Pull up an online graphing calculator to confirm if you're concerned that you might not quite have it right. You can see whether or not it actually gave you the graph you intended for it to give you. Any questions on this one? All right.